In 3.7, we cover elasticity of demand. This is another application of derivatives, and most students feel much lighter application than what we saw in 3.6. So it's nice to end chapter 3 with this section. Let's take a look. What is elasticity of demand? It turns out this is an economics application, and it takes a little bit of building up. First thing we're going to talk about is relative rate of change. So relative rate of change, you see how it's defined there. It's your rate of change divided by the original value. And what that would look like in a formula, well, the rate of change is described by a derivative, f prime of x, divided by, and the original value is described by, well, the original function, f of x. So we put those together and we call it the relative rate of change. What we're thinking of is, hey, how fast is our value changing, but then relative to what the actual function value is. So let me just give you a really quick example. Let's say, you heard that gas prices are decreasing 10 cents per week. So that would be like a rate of change, right? Gas prices are going down by 10 cents per week. And we'd all think, oh, okay, that's great. 10 cents a week, that's huge. And we'd all be really happy. Compared to what if someone said, hey, you know what, the value of your car is decreasing by 10 cents per week. Okay, same thing, but now make it a car instead of gas prices, but still going down by 10 cents per week. And you think, well, that's no big deal. Right? So I know my car is going to lose value as I drive it. It's, if it's decreasing at 10 cents per week, well, probably, any car out there is probably worth a couple $1,000s at least, if not several $1,000s. So if it's only decreasing at 10 cents per week, that's not very much at all. Where we might think the gas price is going down at 10 cents per week is a lot, a car going down in value 10 cents per week is next to nothing, right? That's at the end of a year, that'll only be about $5 or something, right? So that's virtually no. Okay, so it's all relative, right? So how much is it, increasing or decreasing? But then we compare it to what the value itself is. We call it the relative rate of change. All right. Very similar to that, we've got the percent rate of change. And the only idea here for the percent rate of change, we take the relative rate of change and multiply it by 100, and that turns it into a percentage. Okay. So let's take a look at some examples, or one example anyway. Find the relative rate and percent rate of change. We'll start off here with part A. Let's say our function is 60x minus 1.2x squared. We're going to find this relative and percent rate of change at x equals 5. Okay, so we'll go with our formula. So we can see we need a derivative to do that. So first thing we can do is find the derivative of our function. So in this case, it would be 60 minus 2.4x. And we can think, okay, so for the relative rate of change, I'll take the derivative and divide it by the original function. And all right, so there's our formula for the relative rate of change for this function. And then, okay, we want to do this at x equals 5. So let's go ahead and plug in 5. So we'll plug it in to the numerator, plug it into the denominator, and you can see plugging in there, and we end up with 48 over 270. Now, I kind of did this in this way where I set it up as this ratio first, then plugged in. We could certainly do it in a different way. We could find f prime of 5, that's 48. We could find f of 5, that's 270, and then make the ratio. Either way, 48 over 270, we want to think of that as a decimal. and it turns out it's 0.178. And let me just check. Did I round that, or did that come out? Yeah, I rounded that. So 3 decimal places. I think that's pretty good. Okay, so if the relative rate of change is 0.178, we also want to find the percent rate of change, but turns out we've done most of the work already. All we need to do is multiply that decimal 0.178 by 100, and we've got it 17.8% rate of change. And maybe depending on the circumstances and the context, right? A percent rate of change of 17.8, or the equivalent relative rate of change 0.178, that might be a lot. Wow, it's increasing at 17.8%. Like, that might be huge, or maybe in another context, it's not so much. Let's try one more. Mix up our function just a little bit. Let's say our function f of x is 9x minus 5 natural log x at x equals 3. Let's find the relative rate of change and the percent rate of change. Well, first thing we're going to need is a derivative. So here the derivative is 9 minus 5 times 1 over x, or maybe we prefer to think of it as 9 minus 5 over x. And then, well, I'm approaching it in the same way. I'm just putting that derivative function divided by the original function. And then I'm going to plug in the 3. Of course, you could plug in the numbers, the 3 to each of the original and the derivative function separately, and then divide. Either way doesn't matter. Notice here, doing it this way, I didn't even bother to simplify these numbers. I just did that all at once. 9 minus 5 over 3 divided by 9 times 3 minus 5 natural log 3, all at once, and there you go. The relative rate of change here, 0.341, which would mean the percent rate of change, well, just multiply by 100, 34.1%. And those are definitely, that relative rate of change has definitely been rounded. No question about it there. 3 decimal places is pretty good. All right. One thing to note here, just as you're doing work, if you're looking in the textbook, looking at homework, you might hear the phrase the logarithmic derivative. That is another way people describe the relative rate of change, as you see right there. You might hear it referred to as the logarithmic derivative. And so just know, if you hear that phrase, all that means is the relative rate of change. Let me explain why. Why would that formula right there, f prime of x divided by f of x, why would that be referred to as the logarithmic derivative? That seems strange. So imagine you've got the natural log of f of x. Well, if you were to take the derivative of that, that would need a chain rule, right? It would be 1 over f of x times f prime of x, which would end up simplifying to f prime x over f of x. And so because it would be the result of this derivative, you hear it referred to it that way. Although you don't have to associate with this with being the derivative of anything. It's the rate of change compared to the value itself. But now you know what's happening if you hear that phrase. Okay. Let's get into elasticity of demand. We've got this idea of relative rate of change behind us, and so we can move forward. The elasticity of demand at price P. So here's the motivation for studying this and where it came from. When will increasing the price increase revenue? Okay, so that's, a huge question for, how different products are priced. Of course, most companies, they want to make the most revenue possible. And so they're going to set their price point in order to achieve that. So maybe increasing the price actually increases revenue. Maybe people are willing to pay more and they're still going to buy it anyway. Um, Although in other cases, maybe they should decrease the price. And even though they drop the price, they end up selling more of these things and their total revenue for the company goes up. It might also help you find, the just the right price to set in order to maximize your revenue, right? We definitely want to know that if we are a company producing, some kind of item. Okay. Here's what we can do. We can define elasticity of demand at price P. We're going to call it capital E of P, the elasticity at price P. And here's where it comes. Here's the formula for it, I should say. It's negative the relative rate of change in demand divided by the relative rate of change in price. So we've got two relative rates of change, one for demand, one for price, and we can set up that ratio like so, and then don't forget the negative goes out front. Okay, let me break it down, not in words, but more in a formula style. Look like this. So E of P equals, okay, we got the negative out front. I'll explain that in a moment. F prime of P over F of P. So think of the demand function as F of P. So that's how many of these items we're going to sell if we set it at price P. And of course, it's a relative, so we put the rate of change in the price, or excuse me, the rate of change in the demand at that price divided by the actual demand. Okay, how fast is the demand changing divided by what the demand actually is. And then all that gets divided by, and now this one at the bottom is a little bit simpler, the rate of change in the price. It's the same idea, except we're thinking the price is P, and that 1 is the derivative of P. So we don't have a function here, it's just, hey, the price is P, and then the numerator, well, the derivative of P is 1. So there's our relative rate of change in the price. Why the negative in front? Why the negative in front? So it turns out if you were to do this whole formula, the result will be negative. Okay, so this extra negative makes it all positive. And so we like to think of the elasticity, just kind of the way we think of it. And to answer this question here, we want that result to be positive. So if we put this extra negative out front, then it'll turn the entire thing positive. Is the idea. Why would this whole thing be negative? Maybe you're asking that, maybe you're not. So the rate of it turns out it's this derivative here. The rate of change of the demand at a particular price. So it turns out if the price goes up, demand is always going to go down. If you raise your price, the demand always goes down. There's always going to be less people willing to buy it if you raise the price even a little bit. Now, the idea is maybe you raise the price and most people are still willing to buy it, and so you end up making more money. But it's always less people that are willing to buy it if you raise the price, never more, or at least that's the theory here. So this is always going to be negative, and so we throw this extra negative out there to make the entire thing positive. Okay. Here's the simplified version. This is great, nothing wrong with this, but a fraction over a fraction, we can simplify that. And we end up with this. So it turns out because our denominator is 1 over P, it simplifies very nicely here. And if you're wondering like, oh, how would we see that? Well, I didn't include this step, but if we're ever dividing a fraction by a fraction, we can flip this over and multiply. flip the 1 over p to be p over 1. And then, okay, when these multiply, you can see it there, negative p times f prime of p over f of p. This is our elasticity of demand formula. That's what we're going to use. Along with that, we should note just what different results will mean. And so let me show you all of this. So it turns out after doing this calculation, if we get a value less than 1, then we say demand is inelastic. What would that mean? Demand is inelastic. So that means if we make our price higher, our revenue is going to go up as well. They say inelastic because it's like there's no give. If you raise your price, you raise your revenue. Raising the price does not deter very many people from still buying it, and so you end up making more money that way. However, if E of P is greater than 1, you do this whole calculation, you get a number bigger than 1, then we say demand is elastic. So there's this like kind of springy sort of effect I'm trying to visualize. Okay, so if you raise your price, then revenue's going to go down. So raising the price, it deters a lot of people from buying it, depending on how much you raise your price, and the revenue then will go down. Actually, let me back up. Raising your price even a little bit will drop your revenue. So it's almost like the price is already too high. So if you keep jacking up that price, you're just driving more and more people away. Where this would say you were not charging enough. So if you raise the price, your revenue still goes with it because people agree it's worth more. If E of P equals 1, then we say it's unit elastic, and the word unit just comes from the fact that it's equal to a 1. Unit elastic is really the ideal. Your revenue is maximized. If you're to do anything, raise the price, lower the price, then your revenue would drop. And we don't want that. So really we want to achieve unit elastic and then hold it. Okay, let's stop this video here. We're going to get to some examples for elasticity of demand next.